Good morning. Welcome to Manish Kumar channel. Today we are going to discuss about the vector space. So before going to discuss, let us review why we need linear algebra. So if you see here the equations, uh, 2x plus y equal to 5, x minus y equal to 1 can be drawn by the line equation and they meet at 2, 1, right? This is called a row picture. When we solve this picture using the column of A, if I create a matrix, if you see matrix A is being created and then column C1, C2 represent 2, 1 and 1 minus 1, then we are going to plot again in the XY axis this equation by column picture. So if you see, this is the question here. V1 is one vector, V2 is another vector. So linear combination, how much linear combination of X and how much linear combination of Y of these two vectors is going to be the right hand side. So this is the solution as X is 2 and Y is 1, right? Now Y column picture is going to help because if you see, we are first going to learn the linear combinations and the birth of vector, right? So now we are going to introduce the vector space. And another reason here is if you see, if I increase the vector system of equations Ax equal to B, let's say n by n dimension, right, and number of unknowns and number of equations. Okay, so in that case what will happen, the geometry is very hard to visualize, right? For instance, if you see 3D, there are so many uh, you know uh, problem in visualizing the where the intersections of simultaneous planes are, we are unable to visualize, right? So in that case, if we move from row picture to column picture, then it makes my life easier because we are going to represent the vector. So in case if I'm going to go for 9 equations, 9 unknowns, then the solution will be very easy to visualize in 9 dimension. Only I have to make, let's say, x1, x2, x1, x9, right? And then this, let's say this vector is representing this, another 9 vectors this, another 9. So there are 9 vectors, 9 equations, and then you are going to see how they are going to meet on some plane or some point and so on, which is very easy to visualize. So, and the solution will be the column vector of R9. Okay, so now R9 is the vector space. So let us understand the vector space. What is vector space? Okay, so vector space is a vector space, or sometimes we call it as linear space, is a set which should be a non-empty. So V should be non-empty, right? Non-empty set together with the vector addition and scalar multiplication, right? Satisfying the following axioms. So let's say for any u v w belongs to v, alpha beta belongs to r, then u plus v belongs to v. That means v is closed under addition, and alpha times of u is equal to, is belonging to v, then it is called the closure property, right? Closed under multiplication, under vector multiplication, right? Because we are multiplying by the vector under, so we call it as closed under multiplication, scalar multiplication. Okay, so another property, if you see third property, u plus v equal to v plus u, called commutative property. U plus v plus w equal to u plus v plus w, that is called associative property. And then we are able to talk about whether there exists any identity element or not in that vector space. So I can see there is an element 0 vector such that I'm going to add to the vector v, and I'm going to get the same vector, right? So left and right, if I'm going to add that vector, I'm going to receive the same vector. So the only possibility is 0 vector. So if 0 vector exists, then we are able to talk about identity element. So how much amount I'm going to add to the given vector so that I will get the 0 vector. So only the thing is that uh, once identity exists, we are able to talk about the inverse, right? If this property is going to be satisfied, we can say that identity exists. Sixth property. Seventh property and eighth properties are distributive. Seventh, eighth, nine are distributive property under vector addition and scalar multiplication and so on. And then last one is the multiplicative identity property. So these 10 property needs to be satisfied for a given vector space. Okay, so now the question is, vector space is always defined over a field. Let's say we say F, right? Where F can be real, F can be complex, F can be rational, F can be any finite field ZP, right? So in our discussion, we are going to talk about only the real vector space. Okay. So now real vector space is denoted as V defined over R is called a real vector space. And how the vector space looks like, if you see, the vector space looks like element. Okay. So if you see that v1, v2, v3 and so on, the elements of the vector space and how elements are being defined. So now important note here, vector space is a, you know, vector space you can think of like a placeholder, like v, then it is going to be holding some values, placeholder, right? And these values will be fielded by the field element, right? That is the meaning we call it as vector space is defined over a field, and without field vector space is nothing, right? You got my point or not? So we have to fill with the vector element, field elements. Okay, and in our case field is the real field. We are going to fill with the real numbers. Okay, so now for example, if you see x, y, z, w's are there, and then the arrangements are in the linear way. So what I'm going to say, x, y, z, w, so this becomes an element of this vector space v1, right, which belongs to R4. So my vector space V is the R4 where one of the element will looks like X, Y, Z, W, right? So vector space just like a placeholder we are going to fill. For example, if my placeholder is just like a matrix type X, Y, Z, W, so we are going to fill the X, Y, Z, W in the matrix form, right? And where these numbers are filled by the field element. So without field vector space is nothing. This is very important remark. Okay, and we can say vector space always defined over a field. This is the final conclusion. Okay, so now for example, R over R, R over R is the real vector space over real field, right? And later we will talk about the dimension in next video. And so vector space, span, basis, dimension, all those things we will discuss in further videos. Okay, and if you see C over R, set of complex plane, right, set of all complex point in the complex plane defined by the real vectors. Okay, real vector space, uh, real field, right? Similarly, set of all m by n matrices defined over the field where field is real, right? We are going to fill like 2 by 2 as I have shown you as an example, right? So important note here, vector space elements might contain abstract elements. Sometimes people have that feeling, okay, only the vectors are the set of all vectors forms a vector space. Answer is no. There are some abstract sets which vector space may contain. So such as collection of functions, equations, matrices, sequences, and so on. We will see some example later. So now V, if we are going to take V as a singleton zero vector, right? So is which is the smallest vector space. You can satisfy all 10 axioms by this vector. If you see, if you can say that 0 plus 0, 0 vector plus 0 vector is going to be 0 vector. So this belongs to V. So V is closed, right? Elements are only 0, so only you are going to pick up 0. Any vector if you take, any scalar if you take alpha into 0 vector, right, is going to be 0. So again belongs to V. So this is closed under addition and scalar multiplication. So this is the smallest vector space, right, with usual addition and scalar multiplication. Okay. Another example is R2 plane x comma y such that xy belongs to R with usual addition and scalar multiplication, right? X plus component wise addition and you see component wise multiplication. This is also forms a vector space, so you can verify all axioms are going to be satisfied. So we call it as this is R2 is a vector space. Now the representation of the vector space, sometimes we write like this: the space, the vector space V, here V is Rn, plus and product with two operation, we call it as a vector space. So Rn is also vector space, n dimensional vector space. Okay. Next example, if you see, set of all polynomials of degree less than or equal to n with the usual addition and scalar multiplication is a vector space, right? And if you take any two polynomial and if you add it, then you will always get the polynomial belongs to the degree less than or equal to n, right? So now if I'm going to restrict something here equal to n, if I say set of all polynomial of degree exactly n is forming a vector space over usual addition or multiplication, answer is no. You can see very quick example. Let's say n is equal to 3, right? I'm going to take a polynomial. So element of this vector space will be a polynomial. I'm going to take, let's say, x cube plus x plus 2. Another polynomial I'm going to take minus x cube plus 2x plus 2, right? If I'm going to add usual addition, if I define usual addition of this vector, right? So what will happen? This will be gone. So I'm going to get only the polynomial which is 3x and plus 4. This is again one of the polynomial, but degree of this polynomial is not 3, right? So in that case, I have taken exactly 3-degree polynomial, but the closure property, if I applied, then this is not going to be the degree 3 polynomial. So this fails actually. Closure property, first property fails under vector addition, right? So this is not a vector space. So in general, I can say set of all polynomial exactly degree equal to n is not going to be the vector space. This is a very, very important point you have to make, right? And then later we will talk about the dimension of this polynomial and all. Okay. So now in other videos actually, so now you have to keep this point in your mind. Okay. Now set of all continuous functions with usual vector addition and scalar multiplication is also a vector space, which is a set of all continuous polynomial defined under the closed interval. Now you can see that we are going to say, let's say this is C01 CAB, right? CAB. Okay, then I can say that if I differentiate this polynomial set of those are the space I'm going to differentiate, right? D1 means first time differentiation. So what had happened, every continuous function need not be differentiable, right? So differentiable space is slightly smaller, right? This is the differentiable space. Okay. Now, if you see, there are some functions which are here, right? They all are continuous but not differentiable, right? So you can also say that, conclude that set of all differentiable polynomial, right, is also continuous functions which are differentiable one time, that is differentiable functions, right, is also forms a vector space with usual addition and scalar multiplication. Now one more point, if you see, if I'm going to say D2, this denote D2. D2 means second time differentiable. Second time differentiability requires at least first derivative will be, this derivative will be continuous. Then I'm able to differentiate. You got my point or not? So second time derivative will be the smaller space, right? So this will also forms a vector space, and so on. We can reach towards like this, right? So you can see that C is a bigger space which contains D1, which contains D2, and so on in that same way, right? So this is the smaller, as long as you are going to reach, you will get into the smaller space. Okay. This is another examples, right? Multiple example I can say. Similarly, if you see set of all m by n matrices over real entries means the field is real actually with usual addition scalar multiplication is always forms a vector space. So now the question, what are the vector space what are the space which are not vector space, right? So if I say set of all real valued functions defined on 0 1, I'm going to restrict with condition, this condition. if I'm not going to restrict this condition, then it will be a vector space by this example, right? Example 4. Now what had happened, if I want to see this is not a vector space, this is not a vector space, then I'm going to say f plus g are two function acting on 1, right? What had happened, f1 plus fg1, right? G1 and f plus g are in f and g are two functions which are in V, then f plus g must be in V. So this is 2 plus 2, which is equal to 4, not equal to 2. So this f plus g does not belongs to V. So V is not at all closed. So now if you look at it here, this condition, if I'm going to say f 1 is equal to right hand side 0, something right hand side 0 with usual addition and scalar multiplication I'm talking about, right? Then what had happened, this will always be true. If I put any constant not equal to 0, then this is not going to be true. So I can generalize this, and whatever value I want to put it here, I can construct multiple problems related to that, right? So this is another no vector space which is not a vector space. Similarly, if you see this picture R2, right? R2 we have seen under usual addition and multiplication is vector space. But if you see the line passes uh, just not through origin, right? Not through origin. So what had happened, zero vector is not there because zero is the identity of R2 0 0, right? So zero vector is not at all here. You got my point or not? So this is not this is not a vector space. Okay. If line passes through origin, right? Any line passes through origin will be a vector space. You got my point or not? Okay, so if you see here, because in this additive identity does not exist in this line. Zero vector does not exist, additive identity. So any one of the axiom is failed, then this is not a vector space. Similarly, if you think of like this plane, like say if I say this plane means half plane above. It means x y greater than 0, y greater than 0. So y greater than 0, this plane. So if I multiply any element here by negative scalar alpha, right? Because alpha is a real vector field element, so alpha can be negative. If I say -2, if I multiply this plane, this point becomes here, right? This direction, which is no longer the space, which will not be in the space at all. So I will again one more point I will emphasize, anything is greater than 0, less than 0, or something greater than 1, less than 1, or something like that condition is there under usual addition and scalar multiplication, then this is not going to be a vector space. Now if I say set of all matrices, 2 by 2 matrices, right, whose entries whose trace trace of M22 is 0, right? Set of all 2 by 2 matrices with trace 0 0. Trace 0. Trace means the matrix, let us take one element 1 minus 1 0 0. This trace of this matrix is 0, right? Trace, if you take trace means sum of the element. Trace of this matrix is, this is let's say A. So trace of A is equal to 1 plus minus 1 is going to be 0, right? Trace is 0. So this belongs to this space, set of all matrices whose trace is 0. Now if you see here, B matrix, I'm going to construct B matrix. B matrix is -1 0 0 1. So again trace of B is 0, right? So this A and B will be the member of V, right? A, B belongs to V, right? But the thing is that what about A plus B? If you see here, A plus B, right? A plus B, if I'm going to say here, is going to be, when you add, this trace will be 0. So A plus B belongs to B. But when I'm going to multiply, right? So this is also going to be, what forms a vector space, because if you see, if you multiply, if you add, if you subtract anything, then it will satisfy all the axioms, right? But if I say here, if trace is 1, if I say trace is 1, let's say trace is 1, right? So you have to think of whether this forms a vector space or not, right? This is one of the important point you have to think of. Okay. Another example is if I say set of all matrices M2 cross 2, right, such that the determinant of this A is going to be 0, right? So what had happened if I'm going to take A matrix 1 0 0 1 and another B matrix, uh, determinant is 0 I want, right? So I have to take this element 1 0 0 0 and 0 0 0 1. What had happened? A plus B will give you 1 0 0 1, right? Which is determinant of A plus B, if I'm going to calculate, is going to be 1, right? So determinant of A plus B is not equal to 0. So A plus B will not belongs to M2 cross 2. So anything like this you have to check. If set of all 2 by 2 singular matrices, set of all 2 by 2 non-singular matrices, all those things will create a problem. So you have to identify whether this is a vector space or not, right? So this is not a vector space. Okay. Now let us do another example. Uh, Vector space V such that xy belongs to R and x is strictly greater than or equal to 0 and x is a subset of R2. So this is basically half plane. So as I told you, if you take any alpha and multiply with negative sign, this plane, this point becomes here, which is no longer in this space. So this is not also a vector space, right? Now let us talk about the unusual vector space. What is the unusual vector? Unusual, I mean, if it is being given to you, add x plus y, I'm going to define my way of addition x plus y minus 2, right? Which is unusual, it seems, because I have defined myself based upon my demand. So similarly, that is what we call it as unusual vector space, because the addition is denoted as this uh, plus circle and dot circle to distinguish with plus and product, right? This is usual, and this plus circle and dot circle is unusual. So how it is being defined? You see, two vectors, all those, V is a vector collection of xy, x greater than 0, y greater than 0 in R2, subset of R2. So x1 comma y1 plus x2 comma y2 will be first component product, second component product. That is why we call it as unusual addition. And similarly, alpha times of x comma y will be x to the power alpha, y to the power alpha for any alpha belongs to real number, right? So this is basically R2 over R is now your V, okay? Vector space defined over the real field. So let us check whether it is a vector space or not, where the condition is x greater than 0, y greater than 0. This is important, right? This is on unusual, right? I've told you if greater than 0, half plane or something like that will not be a vector space in sense of usual addition and scalar multiplication, right? Not unusual sense. So let us see this forms a vector space, right? So x1, let us take 2 points x1, y1, x2, y2 belongs to V. Then their sum will be x1, y1, x1, x2, y1, y2. And since x1, y1, x2, y2 all are greater than 0, and this product is also greater than 0, this is greater than 0, it means this belongs to V. So this is closed under addition. Similarly, the second property, if you check, second property also going to be satisfied. So belongs to V, closed under scalar multiplication. Third property, if you check, third property, associative property, is also going to be satisfied because x1, x2, x3 all are greater than 0. So their product is also greater than 0, right? So this belongs to the space. Associativity property also hold true. Identity, I'm going to find what is the identity such that I'm going to get it add, will get the same element. So identity, if you solve, you are going to get 1 1. So 1 1 is the identity which is not the identity of R2 0 0. Generally R2 usual addition identity will be, additive identity will be 0 0. But since we have defined an usual way, then we are getting different than this identity. So 1 1 is the identity, right? So now if similarly you can find the inverse such that you will get x plus y equal to something 1 1. So now if you see, inverse is going to be 1 by x and 1 by y, right? And similarly, if you say all the distributive properties, all of them are going to satisfy, right? And all 10 properties are going to be satisfied. So we say that this is a vector space under unusual addition, scale multiplication forms a vector space, right? And this binary operation, either plus or dot, can be defined as v cross v to v is a map actually, and f cross v to v, called binary operation. Sometimes we call it as, right? Another example, show that R is a vector space with the following operation. This is also unusual way, right? So now you have to check all the properties, right? So check whether this is a vector space under usual addition and under unusual addition and unusual scalar multiplication or not. So if you try to check, then distributive property is going to be not satisfy you, which fails, right? So this property is going to be fails basically. Okay, these are the operations given. And now the last eighth property. Eighth property of the axiom is not going to be satisfied, right? Okay, so this is not a vector space. And there's a remark, let V be a vector space, then every vector V in V, alpha belongs to V, we have the following uh, result. Alpha times of zero vector is going to be zero vector. 0 times of V is equal to zero vector. Minus 1 times of V is equal to minus 1 minus V. And if alpha into V is equal to 0, then we call it as, uh, either alpha 0 or V 0 or both, right? So thank you.